Exponential rule number 1. A to the m times a to the n equals to a to the m plus n. Here's a demonstration of this rule. So for example, if you have 3 to the 4th power times 3 to the 3rd power, this will be 3 to what power? 3 to the 7th power, because you have 4 plus 3, which is 3 to the 7th power. That's what this rule says. But you can still ask why. Yeah. Why do you add? Not just because. There should be some other reason than that. Can anyone explain why? Why do we end up adding? Yeah? 3 to the 4th power, what does that mean? Yeah, 3 to the 4th power means 3 multiplied to itself how many times? 4 times, right? And 3 to the 3rd power means 3 multiplied to itself 3 times. Now, count how many times you multiplied 3. 7 times, right? Yeah. So that's why you end up adding the exponent. So in other words, this rule is not some rule that mathematicians convened and agreed upon. Rather, it's something that we observe. Like if you start with this notation, 3 to the 4th means you multiply 3 to itself 4 times, then it has to be, it's natural that you end up with 3 to the 7th power. Okay. Now, what about division? So if you have a to the m divided by a to the n, this is a to the m minus n. An example of such would be, say, 3 to the 5th power divided by 3 to the squared. What would you get? According to this rule I just wrote down, this is 5 minus 2, which is 3 to the 3rd. And you can, again, ask why. And the explanation is the exact same thing. 3 to the 5th power means you multiply 3 5 times. 3 squared means you multiply 3 twice. And because if you have same thing on the top and the bottom, you can cancel them out. After cancellation, you see what's surviving is 3 to the 3rd power. 3 multiplications of 3 survives, right? So this cancellation explains why you end up subtracting. Okay? All right, number 3. Rule number 3 is that if you have a to the nth power to the nth power, this gives you a to the, m times n, right? So an example of such would be, say, 2 to the 3rd power to the 4th power is equal to 2 to the 12th power. Why is that? Well, think about 2 to the 3rd power. That's 2 times 2 times 2. And that's being taken 4th power of, right? So if you have 2 to the 3rd power to the 4th power, that means 2 times 2 times 2 is taken 4th power, means you repeat this 4 times. So if 2 times 2 times 2, 2 times 2 times 2, 2 times 2 times 2, 2 times 2 times 2. And it's kind of obvious, like it's pretty soon Halloween. If your aunt prepared 4 bags of candy with 3 candy bars each, how many candy bars do you have in total? 3 candy bars each, and you have 4 bags. What's that? 3 times 4, right? So you can count that if 2s are like the candies, then if you have 3 in each bag and you have 4 of those bags, then this must be 2 to the 3 times 4, which is 2 to the 12, right? So in general, you can you can look at this and say, oh, you have m candy bars in n bags. How many candy bars do you have? M times n. Kind of straightforward, right? Okay. Um, Now, number 4. Up till here, this could be something quite natural, and it's more like an observation than a rule. But then people started to wonder about other numbers you can put as exponents. So first number that you should think about is 0th power. What is anything to the 0th power? Okay, so that's what you were taught. But this is not in the scope of the original definition. Original definition of powers is whatever number you put in here, you multiply this number that number of times, right? So if you have, say, for example, 2 to the 0th power equal to 1, this doesn't make any sense because how can you multiply something 0 number of times? And why do you define it as 1, right? But this is when mathematicians actually had to make an agreement. Mathematicians agree that we should make this as 1, and the reason for that is we want to define this in such a way that all the rules here would still work. Okay? And one example of such is, say if you have 2 to the 3rd power over 2 to the 3rd power. What is this according to this rule? This is 2 to the 0th power, right? And because this is 8 over 8, what's 8 over 8? 1. So if you agree that this should hold even when mn are not positive integers, because only for positive integers we know what it means, right? To make this 0th power sensible, the only way you can make it work so that the previous rules work is if you define it as 1. Okay? So that's why we mathematicians agreed that it should be 1, so that we don't have to change these rules. These rules will still work. Okay? All right. Number 5. Another example would be a negative number. How would you do negative number, negative m? And the answer to this is the same as 1 over a to the m. And the reason for that is because you have, you can do, you can think of a to the 0th power over a to the mth power in 2 different ways. One way is to apply this rule. If you divide, you subtract, right? So on this side, it would be 0 minus m, which is a to the negative mth power. But then on this other side, we know what a to the 0th power is. What is a to the 0th power? 1. So you have 1 over a to the mth power. So if you want rule number 4 and rule number 2 to still be satisfied for when you have a negative exponent, you don't have any other choice than to say that negative power means 1 over. You got that? Yeah. All right. And then last rule is probably the most complicated looking one, which is number 6. If you have nth root, no, if you have a to the 1 over nth root, so this allows you to put fractions in the exponent. Okay? That's same as nth root of a. Now let's think about such an example. Say you have 5 to the 1/3 power. That's a really strange number. It's hard to think about what this is, but what we do know is that, if you take 5 to the 1/3 power and multiply it to itself 3 times, then we have rule number 1, which says multiplication means exponents add up. So you have 5 to the 1/3 plus 1/3 plus 1/3. What is that? 3/3, which is 1, right? Which is just 5, right? Okay. So it's some strange number. If you multiply to itself 3 times, then you end up with 5. But you actually know such a number, although we don't really know it explicitly. We have this concept of cube root of 5, which does the same thing. If you multiply cube root of 5 3 times, that's like cube root of 5 times 5 times 5 is 5 cubed, right? And we know the cube and cube roots cancel each other, right? So these two cancel, and so you end up with a 5 as well. Oh, so they do the same thing. 5 to the 1/3 power is in fact same as cube root of 5 because they have the same property. If you multiply it to itself 3 times, you end up with 5. However, contrary to previous examples, like even here, you can talk about some like 2 to the negative third power would be 1 over 2 to the third power, which is 1 over 8. You can easily imagine these other powers. Like 1 is not hard to imagine. 2 to the 0 power is 1 that's easy to grasp, whereas 2 to the negative 3 is slightly more challenging, but 1 over 8, that's something that we also use in everyday life. So those are not that hard, except that this cube root of 5 is very mysterious. So let me just let's just think about cube root of 5 a little bit more, just to have some grasp of this. So first of all, if you have 1 cubed, that's 1, right? And if you have 2 cubed, what's that? 2 cubed is 2 times 2 times 2, which is 8. So that means since 5 is between 1 and 8, 5 cube root of 5 would be between 1 and 2. Because this is a number, if you cube it, you get a 1. This is the number, if you cube it, you get an 8. And this is a number, if you cube it, you get a 5. So this number should be somewhere in between here and there. Don't you agree? Right? Okay. And then you can investigate further by choosing a number between 1 and 2. So like, let's go with half of 1 and 2. Halfway between 1 and 2 is 1.5. If you take 1.5 cubed, you end up with something like 3.325, 375, 375, I think. Yeah. Okay, so you get that. Okay. Which means cube root of 5 is what? Lesser than 1.5 or bigger than 1.5? What do you think? So cube root of 5 is such a number that if you take a cube, you get a 5. So which is bigger? Cube root of 5 is bigger than 1.5. Isn't that right? Agreed? Yeah. So you try with something bigger, say 1.6 cubed. If you do that, you get 4.096. So cube root of 5 is bigger than 1.6. Okay. So if you keep doing this, you end up seeing that, you eventually you see that cube root of 5 is between 1.8 and 1.7. If you take the cube of 1.7, you get something slightly less than 5, whereas cube of 1.8, you get something bigger than 5. So 1.7 cubed is 4.9 something, and then 1.8 cubed is, I don't know, something a lot bigger, okay? So you get that. And then you can continue on. You can now, next thing to do is like take 1.75 and take a cube, see whether this should be bigger than 1.75 or less. And you keep doing this, and you can get more and more digits of cube root of 5. But the problem with this is that cube root of 5 doesn't have any pattern when you write them in decimals. Such a number is called an irrational number. Irrational numbers don't follow any pattern if you look at their decimals. So you end up with a very mysterious number. You know, it exists somewhere between here. So this is some quantity, 1.7 something. Does anyone have a calculator? Can you do a cube root of, so take 5 to the 1/3 power and see what you get. 5 to the power of 0.3333333. What do you get? What's the approximate value? 1.709975. Okay, yeah. 0.9975. Okay, something like that, right? So that's the approximate value. Now, in practice, you would just need a few decimals. You just need a few decimals because, like, for example, you wanted to build a cube that has the volume of exactly 5 cubic inches. And the question is, what should you make these lengths to equal to? Well, your ruler is not going to be able to handle hundredths of an inch. There'll be a very accurate one. So like 1.7 will be enough. You just take 1.7 inches across, up, and wide, and you end up with a cube that's about 5. That's good enough in practice, right? Okay. Now let me talk about a to the nth power, and you take nth root. We just learned that nth root is same as 1 over nth power, and therefore you end up with m times 1 over n, which is m over n. So that formula is often a nice shortcut to have. Let me just add 2 formulas that we end up using a lot. So this is one. And another thing is, you see, in the rule that we just did, in rule number 5, we said a to the negative m equals to 1 over a to the m. And in many cases, not only you need to know how to go from here to there, you also need to know how to go backwards. So I just want to write the same thing, but in reverse direction. And what this is saying is that if your number belongs to the basement, then it can come up above ground with the only changes needed would be taking the exponent and putting a minus in there. So minus exponent is just indicating it belongs to the basement, not above ground. Okay. All right. So let me give you a few questions using these formulas. Okay. Question A. Suppose you're given cube root of 2 over square root of 2. How do you convert this into a fractional power of a single number? Well, first of all, cube root of 2, that's what? 2 to the what power? 1/3 power. Square root is 2 to what power? Square root. 1/2. It's the opposite of a square, right? See, square root of 2 squared is 2, but 2 to the 1/2, 2. Well, we know that the rule is that we multiply these two numbers, right? So it's 2 to the 1/2 times 2, which is 2 to the first power, that's equal to 2. So they both satisfy something squared equals to 2. They both have the property that if you square, you get 2. So these two are the same thing. Right? Square root of 2 is same as 2 to the 1/2 power. Okay. Once you have that, then when we divide, what do we know? You subtract. So you have 1/3 minus 1/2. And because you need common denominators to subtract fractions, this is going to be 2 to the 2 over 6 minus 3 over 6, and that's equals to 2 to the negative 1/3 power. Okay, so we've expressed this original thing as a fractional power of a single number. Let's try another similar one. B. This time, cube root of 4 times 64 fifth power times square root of 8. Okay. That's more challenging. Let's first rewrite everything in terms of fractional powers. 4 to the 1/3 power. 64 to the 1/5 power. 8 is 8 to the 1/2 power. Right? You have to remember that square root is 1/2 power. But this time you have some trouble with either dividing this with this or combining these two. None of those work because the bases are different, right? See, the rule that if you divide a to the n by a to the n, this is a to the n minus n. This rule is only true when you have the same value for the base. Okay? Well, here, this is 4, this is 64. So something's not right. What do you do then? Well, do you see that 64 is like 8 squared and 8 is 2 to the 3rd power? Right. So all of these are some powers of 2. So what you have to notice is that 4 is equal to 2 squared. 8 is equal to 2 cubed, right? 2 times 2 times 2 is 8. And 64 is 8 squared, which is 2 to the 3rd power squared, which is what? 2 to what power? 6 power, because these two multiply, right? So 2 to the 6th power. And therefore, we can rewrite all of these in the following format. You have 2 to the squared, 1/3 power, 2 to the 6th to the 1/5 power, 2 to the 3rd to the 1/2 power, and use the property that these should be multiplying. So this is 2 to the 2 times 1/3, 2 to the 6 times 1/5, 2 to the 3 times 1/2. Now, how do you multiply a number to a fraction? Only to the top, right? Because regular numbers are numbers that are over ground, right? So if you multiply this with 1/3, this 3 guy is in the basement. This is the overground. So overground people only associate with overground guys, right? So this is like 2 times 1 over 3. Yeah. So this is 2 to the 2/3 over 2 to the 6 times 1/5 is 6 over 5. 2 to the 3 over 2. Okay, and then since well, we can now apply division and subtraction and all that, but instead of doing it that way, I find it more convenient to do it this way. Just if anything belongs in the basement, bring it above ground with negative exponent. So I'm just going to rewrite this as 2 to the 2/3 power times 2 to the negative 6 over 5 times 2 to the negative 3 over 2. Okay. So now nothing is in the basement, it's all above ground, right? But to do that, you needed negative powers, right? Okay, what is the common denominator for 3, 5, and 20? Common multiples, least common multiple. 3 times 5 is 15, 15 times 2 is 30. So if you want to combine all of these, see, because now it's a multiplication, it's an addition of all these numbers, plus negative 6 over 5, plus negative 3 over 2. But to add these fractions, you need common denominators. So we're going to rewrite them as 20 over 30 minus 36 over 30, and then minus 45 over 30. Okay? So I made everything over 30. And if you're wondering how I got these numbers, you just simply have to multiply whatever. See, you have to multiply 10 top and bottom to get 20 over 30. Over here, you have to multiply by 6 top and bottom to get 36 over 30. For this one, you have to multiply 15 top and bottom to get 45 over 30. So you just make common denominators, and now you have, let's see, this is minus 81, so minus 61 over 30. That's the answer. As I was walking around, I noticed a few people asking me what to do with the square root. So think of it this way. What is x squared? X squared is what? X to the second power, right? So what is square root of x? Well, this is x radical with a square root, but because square root is the most widely used type of radical among all the possible roots, like you could have a cube root or fourth root and fifth root and so on and so on. But this one is used so often that people decide to omit this 2 in that case. So we just write it like that. So when you have square root, you have to remember that it's really 2 that's omitted. So you should really think of this as 2 with this. And then if you go back using, well, I see, nth root is same as x to the 1 over nth power, right? So using that, this is always equals to 1/2 power, right? So you should just memorize that as a rule, okay? Anytime you see a square root, how do you convert it into fractional power? Half power, okay? That should be something that you just know. Okay, so in the previous example, we realized that if you have different numbers, then it's hard to put them together. So even before starting to solve such a question, you should try to rewrite 9 as what? 3 to what power? Squared, right? And 27 is 3 times 3 times 3. Do you agree? 3 times 3 is 9. 9 times 3 is 27. So this is 3 to the third power. And that's what you have to do before doing anything else. You want to rewrite this as square root of 3 to the third power over cube root of 3 squared, and then square root of 3, just like that. And then we just discussed why square root is same as 1/2 power, so let's apply that. So you have 3 to the third power of 1/2 power. And this is 3 squared to the 1/3 power. This is 3 to the 1/2 power. Now let's continue on. These numbers multiply, so this is 3 to the 3 over 2. 3 times 1/2 is 3 over 2. And this is 3 to 2 times 1/3 is 2 over 3. This is 3 to the 1/2 power. And do that thing again where you bring the guys in the basement over ground by putting a minus sign in front. Okay? All right. Yeah. And then you see that the least common multiple of 2 and 3 is 6. So 3 over 2 is what over 6? You multiply 3 top and bottom, right? 9 over 6. Okay, 2/3 is what over 6? 4 over 6. Okay. And then 1/2 is what over 6? 3 over 6. Okay. So you have 9 minus 4 minus 3. 9 minus 4 is 5. 5 minus 3 is 2. So you end up with 3 to the 2 over 6. Can you simplify this? 2 over 6 is 1 over 3. The correct answer is 1/3. Okay. Now, this is not the only way to do it. There are several different ways to get the same answer. So I want to show you a few other methods. And all of these are natural. I can't say which one's better. So you can go the same way. We can arrive here, or you can stop right here. And then instead of bringing these over ground, we can notice that they have the same base. So if you multiply these two, add, right? So you have 2/3 power plus 1/2, which is 2/3 plus 1/2 is 4 over 6 plus 3 over 6. So this is 3 to the 3 over 2 over 3 to the 7 over 6. Okay? And now when you divide with the same base, this subtracts. So I have 3 to the 3 over 2 minus 7 over 6. And then when you make this as 9 over 6 minus 7 over 6, with the base being 3, you end up with the same answer as before. So that's another way to do it. Okay? That's another solution. Now, some of you might even look at that number and say, hey, 27 has a square factor. What is it? What's the square factor inside 27? 9, right? 27 is 9 times 3. So 9 comes outside the square root as what? It's 3 squared, so it comes out as a 3, right? So it's 3 times square root of 3 times cube root of 9 times square root of 3. If you do that, then immediately you see that square root of 3 and square root of 3 cancels. And if you rewrite 9 as 3 squared as before, this becomes 3 to the first power over, well, cube root of 3 squared, it's like this. So you can rewrite it as 2 over 3, 3 to 2 over 3. And that's like 3 to the 1 minus 2/3, which is 1/3. Okay, so if you knew this, then this would have been the simplest solution. But it usually is not like this. Usually you have to do all this work. Sometimes shortcuts do exist, but they don't always exist. Okay, so let's think about this question. We have some expression with x and y. It's a fraction. The question is asking you to simplify this, but also express the answer as a non-fraction. How do you make that work? Well, first of all, let's use something that we just learned a moment ago, that square root of 27 is 3 times radical 3, so that square root of 3 will cancel. What is this xy squared to the third power? Well, this is like xy squared times xy squared times xy squared. So you end up with x to how many powers? Third, and y to what power? Sixth power. So you end up with x to the third, y to sixth power, x to the fifth, y squared. And then square root of 3's cancel. So you get 1/3. And what about this one? X cubed over x to the fifth. If you divide, what do you do with exponents? Subtract. So you end up with 3 minus 5, which is -2. What about this one? Y to the 6 divided by y squared. Y to what power? +4, right? Okay. So we're almost there. This is as simple as we can have, but what I don't like is this fraction. Okay. How do you write this as a non-fraction? You make it as what? 3 to what power? -1 power. So by doing this, you made it as a non-fraction and simplify it as much as possible. Okay, let's think about this case. Uh, so 32 and 4, those are powers of 2, right? So instead of 4, you should really write 2 squared. Instead of 32, you should write 2 to what power? 32 is 4 times 8, right? 4 is 2 squared. 8 is 2 to what power? Third power. So what is this? This is 2 to what power? 2 plus 3, 5. Yeah. Okay, so you should rewrite this as cube root of 2 to the fifth power, y squared, and then cube root of y should be y to 1/3 power, fifth root of 2 squared, x to the fifth, y cubed. Okay, then we can, well, I raised it, but this is going to be same as 2 to the 5/3, right? Because like cube root is 1/3 power, 1/3 times 5 is 5/3. And fifth root is 1/5. What's 2 times 1/5? 2/5, right? 2/5. Okay, and then what is 2 plus 1/3? Let's just write it like this. Oh, well, better than this, I think it's better to cancel y squared with squares of that. If I cancel, what do you get? This completely goes away, and then you just get a y left out, right? Yeah, I think this is easier. Right? So what you get is this divided by this. These are the same base, so it's 2 to the 5/3 minus 2/5 over x to the fifth. That still lives there, but then what is this? 1/3 minus 1. Okay, so when you divide this much, you get I realize I should probably use colored pencils. Okay. So you end up with 2 to the 25 over 9 minus 6 over, 25 over 15 and 6 over 15. To the first one, I multiplied 5 top and bottom. To the second one, I multiplied 3 top and bottom. So this is 25 over 15. Second one is 6 over 15. And then I want to bring this upstairs, above ground, by introducing a minus. And then 1/3 minus 3 over 3. 1 is 3 over 3, right? Now we just have to calculate this. What is this? This is 25 minus 6 is 19, so I have 19 over 15 power of 2. Negative 5, and then y to the negative 2/3. That's the answer.